Welcome back to Quantify Your Career. So, in the next couple of weeks, I'll be releasing a full hands on project where we will build an options volatility surface from scratch, both in Python and Excel, so you learn more intuitively on what happens behind the scenes in Python. But first, let's understand what a volatility surface actually is, why it's needed in practice, and what you learn in this project, including some fundamentals which we will explore afterwards. Now, to understand this, start with a single option, which is a derivative. You see the options market price, and you use Black-Scholes formula to solve the volatility that makes the model price match the market price. And that number is the options implied volatility for a specific strike price and expiration date. Now, imagine you do this not just for one option, but for many strike prices and many expiration dates. So for each strike maturity pair, you compute its implied volatility. You place those numbers in a grid. One axis is the strike price, the other axis is time to expiry, and above each point on that grid, you have a volatility value. So if you plot this grid in 3 dimensions, the shape you see is the volatility surface. Now, in textbook Black-Scholes, volatility is just one constant number. But in real markets, that is not what you see. Across strike prices, implied volatility bends into a smile or a skew, and across maturities, it forms a term structure. So if you are pricing options at different strike prices and expiry dates, hedging a portfolio of options, or even backtesting strategies that roll options over time, you need to know which volatility the market is implying for each strike maturity point. And now this volatility surface is the tool that lets you look up that volatility, price consistently, and also compare different parts of the curve. And additionally, it also helps you run scenarios by shifting or reshaping the surface. So for example, you can compare a 1 month out of the money option to 6 month at the money option, or test how your portfolio behaves in a scenario where short dated volatility spikes while long dated volatility stays stable. So in the upcoming project video, we will build one complete surface end to end. So the way we'll do it in Python is we will take a set of option prices across strike prices and maturities, implement the Black-Scholes pricing function ourselves, and manually solve for implied volatility using a numerical root finder. We will then organize these implied volatilities into a strike by maturity grid, apply interpolation to smooth the surface, and visualize it as a 3-dimensional plot. And that's your volatility surface. Similarly, in Excel, we'll mirror the same logic. We will set up Black-Scholes with cell formulas, use goal seek or solver to back out implied volatility from the market prices, build the same grid of implied volatilities, and finally create a surface chart so you can see the shape directly in a spreadsheet. So by the end, you will not just have seen a volatility surface, you will have built one yourself in 2 different environments and understand the intuition behind that. And then once the project is complete, we will use the surface as our starting point to learn the theory behind it. So we'll talk about why models move from a single volatility to a stochastic volatility, how Brownian motion and log normal price dynamics enter option pricing, and how stochastic differential equations and tools like Ito's lemma connect a volatility process to option prices. So the idea is to first build something concrete that works and give you a hands-on project experience, and then unpack the mathematics that sits underneath it. If you would like to understand options in a way that connects real market data, code, spreadsheets, and eventually stochastic calculus, I would be happy to have you follow along with this volatility surface project when it releases. Stay tuned for more. Until next time.